Yeah, we are trying to graph these parametric equations. Okay, and we are doing a detailed analysis. So we found the point of intersection, self-intersection, and now we are doing a derivative analysis. Let me mute everyone. Okay, so we found dy dx here, which gives us the slope of the tangent line. All right, so again, this thing describes rise over run, dx dy, change in x, change in y over change in x. And it's the ratio of the change in the t derivatives, the change in y as t changes over change in x as t changes. And we got this function. All right, and now let's see what we want to do with this derivative function. Part C, notice that the derivative itself is parametric. It's in terms of t because x and y are in terms of t. Now for part C, we want to use this derivative to see when slope is, when the tangent line is horizontal and when the tangent line is vertical. So determine when and where. So when we say when, that means you have to find t. Where means that you have to find position. You have to find x, y. C has a horizontal and a vertical tangency. All right, so horizontal tangency, if you remember from calculus 1, is when the derivative is 0. That's when the slope of the tangent line is 0. Yeah, we're gonna set dy dx equal to 0, and that's gonna give us the t value for when we have horizontal tangency. Okay, so here our derivative function is 3t squared minus 3 over 2t. Setting that equal to 0 means that the numerator of the fraction has to be 0. Okay, yeah, a fraction is equal to 0 if the numerator is 0, because 0 divided by anything is equal to 0. Okay, so solve this equation for t. And by the way, just a little bit of a technicality, if the derivative has a common factor on top and bottom, make sure you cancel that out. Okay, make sure that when you find the derivative, you completely reduce the derivative. Here, this is not reducible. There are no common factors on top and bottom. Okay, but what would happen if there was a common factor? Can anyone tell us what would happen if, for example, there was a t on the top? A whole, okay. All right, so Nicholas, you would be right if you're graphing a function, this is the derivative. that has a rational function that has a common factor on top and bottom. This is a derivative. This is not a function of y equal to f of x. This is a kind of a hard question. I don't expect people to answer it. Imagine there was a common factor, dy dx and dx dt. I'm sorry, dy dt and dx dt. Imagine they have a common factor. Then there would be a common zero. Guys, make sure you're listening. Okay? I don't think we're going to encounter such situation, but I still need you to learn. Imagine there's a common factor. So imagine there's a t on the top as well. Okay? Or let's just say there's a t minus 1 on top and bottom. Then 1 would make both dy dt and dx dt 0. There would be a common 0. A common factor means there is a common 0 or a common root. In that case, the curve would not be smooth. Remember, if dx dt and dy dt are simultaneously 0, then C is not smooth. That was a requirement. And that is not happening here because these can't be simultaneously 0. There is no common root. We don't have to worry about it. But in case if that happens, you wanna reduce and then solve. That's not gonna happen with our questions, but just saying. Anyway, nothing funny is happening here. Set the top equal to 0. You can factor this out to 3 times t squared minus 1. Okay, you can factor t squared minus 1. You get t plus 1, t minus 1 equal to 0, which gives us 2 solutions for t. We get t equal to -1, and we get t equal to 1. Okay, so at these t values or time values, derivative dy dx or slope of the tangent line is 0. Okay, that is when. Now, if you want to find where, you have to substitute these into your parametric equations. Again, here are the parametric equations. Let me copy those. And we want to substitute in those t values to get x and y. So here x at -1 is equal to -1 squared, which is 1, and y at -1 is -1 cubed minus 3 times -1, which gives us 2. Okay, so when t is -1 at 1, 2, there is going to be a horizontal tangency. Likewise, when t is 1, x is going to be just 1 squared, which is also 1. Y at 1 is 1 cubed minus 3 times 1. That's equal to -2. Okay, so to summarize this information, points of horizontal tangency are at 1, 2. Yes, at 1, 2. And this happens when t is equal to -1. And we have also at 1 for x, -2 for y, when t is 1. All right, this is going to help you tremendously with the graph. All right, we know where the local maximum happened. Okay. Yeah, now we are going to find points of vertical tangency. All right, can anyone tell me how to find those points? How to find when and the locations?
When the denominator equals 0.
Yes, exactly. You want the derivative function to be undefined, okay? And derivative is undefined when the denominator is 0. Okay, so again, here we want dy dx to be undefined. Okay. Yeah, so let me write down also what dy dx is. Dy dx that we found is 3t squared minus 3 over 2t. We want this to be undefined, so you set the denominator equal to 0. Okay, and that gives you t equal to 0. Okay, so if you want to find the point or the location, plug that into x and y's. X again is t squared, so x of 0 is 0 squared, which is equal to 0, and y at 0 is 0. Yeah, and use the definition for y, it's t cubed minus 3t. 0 cubed minus 3 times 0, that's equal to 0. Okay, so vertical tangency is going to be at 0, 0 when t is 0. Again, this is going to significantly help you with the graph. Okay? Any questions so far? I hope that made sense. Okay, so the next step is the orientation analysis, direction analysis. And again, I doubt the book does this, but it's really cool to learn. Yeah, so D, we're gonna perform a sign analysis. On dx dt and dy dt. So again, dx dt describes motion in the horizontal direction, dy dt in the vertical direction. They tell you if the particle is going left, right, up, down. That's going to tell us what the orientation is. Okay, we are doing a sign analysis on derivative functions. So what you have to do is you have to find the 0 of each derivative. Remember, anytime you do a sign analysis, you need to know if the sign is going to change, sign changes or sign might change at 0 of the function. Okay, so we have to find the 0 of these derivative functions. And all you have to do is just set each of them equal to 0. Here dx dt. We found that dx dt here is equal to 2t, set that equal to 0. And that gives you t equal to 0. Okay. So the horizontal movement might change when t is 0, and then dx dy dt. Again, this was 3t squared minus 3, set that equal to 0. We've already solved these when we found when dy dx is 0, that's when dy dt was 0. But again, that factored out, you get 3t minus 1, t plus 1 equal to 0, which gives you t equal to -1 and t equal to 1. Okay, so motion in vertical direction might change when t is -1 and 1. All right, now, next thing that you have to do is draw a number line and check the sign of each derivative over intervals of t or time. Okay, again, here t is not really time because t could be negative. T is just, again, t is just a parameter. Okay, so here is that number line. This is a two-dimensional analysis. It's a two-dimensional sign analysis. All right. Yeah, so this is the t-axis, by the way. This is not x or y, it's t. All right, and what you do is locate those zeros on the t interval. We have -1, we have 0, and we have 1. Okay, so what these numbers do is that they divide the time interval into, of course, 4 intervals. We have the interval from -infinity to -1. We have the interval from -1 to 0. These are t intervals. We have the t interval from 0 to 1 and the t interval from 1 to infinity. You don't have to draw, you don't have to write those intervals if you don't want to. The number line, the t number line is good enough. Okay, now we're gonna check, we're gonna check the sign of dx dt and dy dt. Again, if you want, you could call that x dot. Dx dt was 2t. All right, we have dy dt. All right, now this is dy dt, and we're gonna do a sign analysis on it. It is easier that you write dy dt or any of those derivatives in factored form. It's easier to do sign analysis on factors rather than the original. It's up to you. It doesn't really matter at all. Okay, writing the factor form makes it easier. Okay, again, you could write that instead. Okay, no one cares, honestly. All right, and what these tell us, again, is direction in X and in Y. Okay, so here in these rows, we're gonna write down the direction for X and the direction for Y. As I said, this is a two-dimensional sign analysis. Okay, so let's do it. What you have to do is pick a number or a test point over each interval. Please do that in your head. All right, so for example, over this interval, you can test any number of your choice. You could pick -2, you could pick -10, -1,000,000, whatever you want. Pick a -2, let's say, okay? Putting -2 in this function gives us a negative dx dt. Does it make sense, guys? Here, I'll just write it down. Test. These are our test points. We test -2 here. 2 times -2 is negative. We don't care what the value is. We just want the sign. Okay, dx dt negative means that motion is to the left. All right, so x is going left. We talked about this in the beginning. Okay, you can choose a number, and let's see, should we do, yeah, let's just do dx dt first, and then we'll do dy dt. Over the interval from -1 to 0, you can test, like, let's say -0.5. Okay, put that into dx dt, you got 2 times -0.5, that's still a negative, which means that the motion is still leftward. Okay, here we can test 0.5. 2 times 0.5 is positive. Motion is to the right. And over this interval, you can test, say, 2. Put 2 here, you get 2 times 2, that's a positive 4. Positive, right. All right, and guys, please stop me if you have questions. Now, we're gonna take those test points and plug them into dy dt to determine a sign. So let's say we take -2 and we plug it into t here. Here we get a -2 minus 1, that's a negative. -2 plus 1, that's a negative also. Double negative is a positive. So what does that tell us, guys? A positive dy dt again. What does that mean? It's going up.
North, yeah.
Yeah, y is increasing. Increasing y means upward. All right. Take -0.5 and plug into your factors. You got negative here. -0.5 minus 1 is negative. -0.5 plus 1 is a positive. Negative times positive, that gives us a negative dy dt, which means motion is downward. All right. Take 0.5 and plug that here. You get 0.5 minus 1. That's negative. 0.5 plus 1 is negative also. Double negative is Is that right? Let's do that again. 0.5, right? 0.5 minus 1, that's a positive, or negative, sorry. Negative 0.5 plus 1 is a positive. So negative still downward. And then 2, plug 2, you have 2 minus 1, that's a positive. 2 plus 1 is a positive. Double positive is positive, meaning that the motion is upward. Any questions on the sign analysis? Upward, downward? How did I plug in? How did I determine signs? Anything you might want to ask? Don't be shy. Are we good? All right, so finally, this tells us what's happening with the curve. Okay, this is going to give you the sign of, or the motion or orientation of C. Okay, yeah, so over this interval, the movement is up, left. What is that? North, west, which is this direction. Okay, like put these two arrows together, that gives you this direction. So I guess they call it the superposition of the two. All right, over here we have left, down, southwest, or west, south. So it's this direction. Does that make sense, guys? This is the left, down direction. Over here we have west, south, or we have right, down. Right down is this direction. And then here we have up, right, north, northeast. It's that direction. Okay. If this is confusing, you can use these two arrows to get this arrow. What you do is you begin with the end point of, so let's say this is called the end point of one arrow. Connect the end point of that arrow to the head of the other arrow. Okay, that gives you the direction. Like over here, you have the tail of this arrow to the head, tail to head, gives you that direction. Tail to head, that's that. We have tail to head, it's that arrow. Again, if you have questions, let me know. If you're too shy to ask me later, or just ask now. We are done. We are really done with all the analysis that we can do. Now we can draw the graph. Last step, step E. Graph C, and you're graphing with orientation, okay? All right, so again, when we are graphing X versus Y. There is no T that can be graphed. Okay, we're graphing position. And let's go back and let me just number my axes. Okay, so let's go back and see what we found, starting with part A. Okay, so part A was about the point of self-intersection, and that's happening at 3, 0. Okay, and you can also label the time values, the t values. The t values that correspond to this position are -√3 and +√3. Okay, if you label the t values on the graph, that's going to help you with the orientation. Okay, you don't have to label these, but again, if you label them, it makes it easier for you to understand orientation. We've already done the orientation analysis, but this is even more help. Okay, so 3, 0 is right here. This is where the curve is going to intersect itself. You can draw an X right there, X meaning it's going to intersect. All right, and again, I'm just going to label my t values here. This is corresponding to t of -√3 as well as t of √3. Okay, so that's part A information. Part B, or part C, part B was just a derivative. Part C, we have the points of horizontal tangency, which happen at 1, 2, when t is -1. Okay, so 1, 2 is right there. Okay, here we have horizontal tangency. Okay, and again, this is corresponding to t equal to -1. Okay, so what this tells us is that at t -√3, the point, the curve or the particle is here, and then later, where t is -1, the point will be there. So orientation seems to be that way. And that's consistent with what this says. Y'all see that? Yeah. We have another point of horizontal tangency, which happens at 1, -2. And this is at a later time, which is t equal to 1. Okay, 1, -2 is right there. Horizontal tangency corresponding to t equal to 1. All right. Point of vertical tangency is at 0, 0. The origin right there. Okay, and this is happening when t is 0. So 0, 0 right there. We have vertical tangency at that point. Again, this is corresponding to t equals 0. Okay, so I mean, look at that, guys. Look at how consistent this is with the orientation. Okay, at t equal to -√3, we are there. At t equal to -1, we are here. Then at t equal to 0, we are here. At t equal to 1, we are there. Okay, and then later, which would be t equal to √3, we are back to this point. This is the orientation. Okay, yeah. So yeah, let's see. Let's do part the last part. Draw the curve with orientation. All right, so from -∞ to -1, these are t values. Orientation is that way. Okay, which means that the curve the curve has to come. Actually, let me switch these two. No, it's okay. I was gonna switch these t values. So what happens is that as t increases from -infinity to -1, the curve is gonna have to go, of course, through that point. It has to go through that point, and it has to go this way. Okay, meaning that you can't draw the curve like that. You can't. Direction has to be always that way, okay? And we have to go through that point. So it just makes sense to draw the curve like that. Okay, there is just no other way for me to draw the curve. There is not. Okay, so yeah, just keep increasing until you get to t equal to -1, where there is a horizontal tangency like that. Okay, and then from t of -1 to t of 0, from -1 to 0, orientation is going to be that way. That way. So here we have to turn, touch that horizontal tangency, turn, and go with that orientation. Like that. Okay, here we have vertical tangency. There is no other way to graph a curve. Vertical tangency. And then at t of 0, orientation changes to this direction. Okay, so we're going to turn and go that direction. Until you touch t of 1, another horizontal tangency. Okay, so again, that arrow is consistent with what this says. Okay, touch the horizontal tangency and then change direction, change orientation to that direction. And go through again the point of self-intersection and just keep going in that direction. That's it. And the curve has got to be a little smooth at those horizontal tangencies. Not so good at drawing stuff. So again, that corresponds to this piece. Okay, this corresponds to this arc. That corresponds to this arc of C, and that corresponds to this arc. We can actually get a so someone might ask, hey, what if the curve does that? It's not gonna, guys. It's not gonna change concavity. There is no way for it to change. If it changed concavity, then orientation would change also. So you could do a second derivative analysis also to make certain of this, but this is ample information.
So I have a question.
Yes, we are, Ahmed. We are gonna do A, B, C, D, E. Yeah. Yes, Luca.
So with like traditional functions, there are rules like the horizontal test, and obviously this doesn't apply to this. But are there any rules like that with parametric function?
What kind of test?
Like the horizontal test where you can't. Oh, sorry, the vertical line test where you can't have.
Right? No, they don't. They don't apply to these. These are the vertical line test applies to functions that are relations that are in this form, y equal to f of x. That's for the non-parametric version.
Right.
Yeah.
So there's no other tests for this, like there's no other restrictions for the parametric.
No, they're not.
Okay,
See, the parametric equations are designed so that we are able to come up with equations that curves that don't pass the vertical line test. Okay, it's impossible to graph this curve using y equal to f of x. You know?
Yeah, that makes sense.
Yeah.
Thank you.
The parametric equations are still functions. They're still functions, but they generate graphs that don't pass vertical line test. Yes, so Ahmad is asking, are we gonna have part A, B, C, D, E on the test? Yes, you bet. And your test is gonna have like 3 or 4 questions, man. I've put this type of question on every test in Math 8. Every Math 8 class that I've ever taught had one of these questions on it. Every.
You're referring to the final, right?
Final or exam 4. I think, yeah, I will put this on a final. And guess what? Out of like maybe 1,000 Math 8 students that I've had, maybe if I'm not exaggerating, only maybe like 10 people did just some parts of it. And I mean, they still did the question, but they skipped like or they made a mistake on a couple of parts. Out of 1,000, let's say every 1,000 Math 8 student that I taught, I would say 990 of them nailed this question. And if you feel like, oh, you didn't learn, trust me, you're eventually gonna look at it and say, oh yeah, that makes sense. Yeah, do this question again on your own. It's really cool. All right, cool. So let's move on from graphing and talk about distance. Yes, arc length. Okay, so assume there is a particle that moves along this path. All right, so you could just ignore, let's say, from -infinity to 0. Let's say there's a particle that is moving on this path along the path like that. And a good question would be, what is the distance traveled by this particle from, like, let's say t equal to 0 to t equal to 1? How much did the particle move? Or how much distance has been traveled from 0 to √3? Okay. Or from 0 to 2. I don't know where 2 is going to be. That's called arc length. Okay. I believe if you took calculus 1, they did arc length in non-parametric form. We're going to do arc length in parametric form, which is more applicable because it relates with time. This is arc length dependent on time, dependent on t. It's applied to motion. Okay. Yeah. So in calculus 1, someone gave you the graph of some function y equal to f of x. Okay. This is the x-axis. This is xa, and this is, like, let's say xb. And you found the arc length from A to B, from x equal to A to x equal to B. Now we are doing this from t equal to A to t equal to B again, which makes more sense. We want position to depend on time. And Jose was asking, am I gonna ask you to do a sign analysis like that? Yes, Jose, yeah. A 2-dimensional sign analysis, yep. Again, no, mind you, you don't really need the sign analysis to figure out the orientation. You don't, because the orientation is very clear. negative root 3, negative 1, 0, 1, root 3. As t increases, you're going this way. That motion makes sense, but I still want you to learn the sign analysis. Okay, so let's talk about again arc length. And I'm going to derive the arc length formula for you, of course. All right, so let's say we have parametric equations, x equal to f of t and y equal to g of t. These are continuous functions, let's just say, and assume that these parametric equations generate this parametric curve. Or again, if we are talking about motion, this would be the path of a particle. Okay, let's just say that this point corresponds to t of a, and this point corresponds to t equal to b. This is the curve, and let's just say this is the orientation. Okay, again, we want to figure out the length of this arc from this endpoint to this endpoint, corresponding to those t values. Okay, well, length means distance, and we all know how to find distance. In R2, we use Pythagorean theorem. Nothing else. Pythagorean theorem. Pythagorean theorem is used on right triangles, right? And this is not a linear path. If I had a linear path like that, I could just use the distance formula. All right, but that's not what's going on. I don't have a linear path. So what you do is you're gonna zoom into C. Zoom in long enough. See, when I zoom in long enough, I no longer see a curvature, right? The curvature becomes almost zero. It's not zero, but almost. You have a line, like look at just that segment right there. That looks like just a segment of a line, right? So let's assume I zoom in long enough and take, let's say, this much of C. Let's do that again. All right. Yeah. So again, this is like a segment of a line. And I can, by the way, here, let's do this. Let's call S, if you don't mind. We're gonna call S to be length of the curve C. Okay, that's what S is used for in this book. Sometimes certain books call it L, which makes more sense, but our book calls it S. A lot of books call it S. So again, S is how much you go from here to here. Okay, now this is just an increment of length. This is just an increment of S. So we're gonna call it delta S. Just a small change in length, okay? Remember, any increment is denoted using delta. Now we can construct a right triangle, okay? A right triangle with a horizontal leg and a vertical leg. Do that again. All right. So since this side of the right triangle is parallel to the x-axis, we call that delta x. I mean, look at that. That is just a small change in x, okay? We're talking about this length of x. So that's delta x. And the vertical side of it is parallel to the y-axis. That itself is a small change or an increment of y. Okay, so that's again our delta x, and this is delta y. You have a right triangle, two legs are those deltas, the hypotenuse is delta s. You can use the Pythagorean theorem on that right triangle and say delta s squared is equal to delta x squared plus delta y squared. All right. Yeah. Again, this is just Pythagorean theorem. C squared is equal to a squared plus b squared for any right triangle. Okay. Now, this is the non-parametric form. Okay, this here you just see an increment of a length, you see an increment of x and an increment of y. This doesn't have an increment of time. We want to introduce the change in time. Okay, so what you can do is you can divide everything here by delta t squared. Okay, given that delta t is not 0. And that gives you delta squared over delta t squared equal to delta x squared over delta t squared plus delta y squared over delta t squared. This is just an equation. You can do whatever you want with that equation. All right. And remember that we are trying to find length. We are trying to find length, which is s. All right, so what you can do, you can take this equation and multiply everything by delta t squared. I want to solve for s, so I need to retrieve delta s. Okay, get rid of this delta t squared by multiplying the equation by delta t squared. Okay, and that gives us delta s squared equal to. Now, also, if you don't mind, I am gonna write delta x squared over delta t squared as the square of delta x over delta t. Okay, I can rewrite that as delta x over delta t, the whole thing squared, plus delta y over delta t, the whole thing squared. Now, as I said, we're multiplying by delta t squared. Okay, and since we want s, I have to solve this for delta s. All you got to do is just take square root. So delta s here is equal to square root of delta x over delta t squared plus delta y over delta t squared. And when you take the square root of this delta t squared, it's just gonna give you delta t, absolute value of delta t, but here these changes are positive, so we just get delta t. Okay, so this is how you can represent an increment of length. Okay, you can represent increment of length in terms of these ratios. Okay, change in x over change in time squared plus change in y over change in time squared times change in time. All right. Now the question is, how do you find the whole arc length? Okay, well, what you can do is you can break up this arc into many delta s's. Here you have one delta s, you can call that delta s1, delta s2, delta s3, delta s4, and so on, and add them up. Add up all the delta s's. You do a summation. Okay, and if you want to get the exact arc length, you're going to take the number of these delta s's to infinity. The more and more delta s's you have, the better you have. If you have a sum or a Riemann sum, when you take the number of partitions to infinity, you get the integral. Okay, so to find s, we do the integral from t equal to a to t equal to b of, now when the number of partitions go to infinity from calculus 1, what happens is that delta x becomes a dx, delta t becomes a dy, delta x becomes really, really small. Okay, the more delta s's you have, look at that. The more of those delta s's you have, the smaller dx and dy become, and a very, very, very small delta x is called dx. So that becomes a dx dt squared plus delta y over delta t becomes dy dt, and that delta t becomes dt. So yeah, I skipped over writing the Riemann sum and then taking the limit of the Riemann sum. But integral means exactly that. It means you're adding up, you're summing up all of these delta s's. Okay? This is the formula for non-parametric or for parametric arc length. And remember, guys, do you remember seeing that before? Who doesn't remember that? Can someone tell me, where have you seen this? I think it was like 2 days ago or last week, late last week. In this class, okay? Let's see. Right there. Does that look familiar? Ring a bell? That's one of the conditions for smoothness. Okay, one of the conditions for smoothness says that dx dt and dy dt should not be simultaneously 0, or it means that when you square them and when you add them, you should have a positive sum squared. That's why I intentionally wrote this condition this way. Okay, we want this to be, when we calculate arc length, we want the term under the square root to, of course, be non-zero or positive. Because if this thing is 0, you're not going to have arc length. Smoothness is a requirement for arc length. All right, so let me just write the arc length theorem, and then we'll do examples tomorrow. So what I just showed you is a non-rigorous proof of where the arc length comes from. And it says let C defined by x equal to f of t and y equal to some function of t g of t be smooth. Okay, smooth on the t interval t from A to B, because we're trying to find arc length over that interval. Okay, so again, we need smoothness, guys, because if C is not smooth, then these derivatives would be undefined. Okay, if one of these is undefined over this interval, then how the heck are you gonna find the integral? These have to be defined, else we are not able to find the integral. Also, the requirement for smoothness says that this should be positive. Okay, if this is zero for by any chance, if that's simultaneously zero, then arc length is gonna be zero. It just makes no sense. We need smoothness. So that's one requirement. Also, we want C to be simple. No intersection. Simple or closed simple. No intersection, no overlap. Because imagine again, the circle example, imagine you are trying to find the circumference of a circle. If the circle overlaps itself, right? If there is an overlap, then what you find is over what the value is supposed to be. You're counting the length twice, I guess, you know. You're not gonna get the correct answer for arc length. So we need smoothness and we need simple. And C has to be simple on the t interval from A to B. Okay, so smoothness on the open interval A to B. We want simple or closed simple on the closed interval AB. And the theorem says that the length of C on the interval AB is that integral that we just derived. Integration is with respect to t. Okay. It's a very simple calculation. This integral is not going to be difficult at all to calculate for our homework problems. But we'll do examples tomorrow. And then tomorrow we're gonna cover the surface area of revolution. But I'll see you then.
Professor, this is still 10 point.
Yeah, this is
right?
still 10.2. This is such a long section.
Okay.
It's a never-ending section.
Thank you.
All right, guys, have a good day.
Professor, quick question. Where can we get up to on the homework? Because I got up to 15 and then realized I didn't learn the rest.
Right, so in the homework, you could do every problem except for the ones that ask for the surface area of revolution.
Okay.
Yeah, I haven't done arc length problems like examples yet, but since you know the formula, if you can apply the formula to arc length problems, just go ahead. You know, all you got to do is take the derivatives. So find dx dt, find dy dt, square them, add them, take the square root, and then take the integral. of it. If you want to hold on to those problems, then you can just wait till tomorrow. But you can do every problem except for arc length and surface area.
Okay, thanks, Professor. See you tomorrow.
Yeah, unless you want to do arc length problems.
Yeah, got it.
All right.